integration. Yeah.
There's a mute button here.
Is that better? So I was saying that I have only 5 lectures, so it will be hard to lecture on all the material that I would like to present. So today we'll speak, we will explain what Motivic integration is. So when you do integration, you have two domains. You have the space that you measure, where you do integration, and it takes value somewhere, usually in a ring. And the p-adic integration, as I explained, took values in the real numbers. But here we will take values in some somewhat stranger ring. And I will start by introducing this ring. So let's take K field. And I consider varieties over K. So it's a category. So schemes of, I mean, apparently not everybody uses the word variety with the same meaning. So let's say schemes of finite type over K, separated and reduced. Okay, it doesn't matter so much, in fact.
Could you try to write figure?
Yes, I can try. And we consider this Grothendieck ring. So you first define it as an abelian group, So it's the quotient of the free abelian group on isomorphism classes of varieties. Okay. By some relation. And these are additivity relations. In fact, I already wrote such an additive relation for the Euler characteristic. For S prime closed in S. So that's this way you get an abelian group. And you put a ring structure induced by the Cartesian product of varieties. In fact, this kind of construction can be done in a much broader generality. Instead of being over field K, you can be over a variety, for instance. And also, you can do similar constructions for any first-order theory. In this way, you can get interesting invariants. There are also cases, like the p-adic case of when you take the K0 of a definable set of a QP, then by a result of Kluckers and Haskell, it's trivial, so you don't get anything. Okay, here you have a lot. So you can view this ring as a universal additive invariance and multiplicative also. So I will not write it on the blackboard, but each time you have an additive invariant, this means that an invariant means that it's the same on, it has value, say, in a ring. The value depends only on the isomorphism class, and it satisfies such an additivity relation. So the value on S is a value on S prime plus the value on S minus S prime, and also that relation. Then, of course, it's tautological that it's uniquely factorized through this Grothendieck ring. Okay? So let's give examples of such invariants. So we already gave one for K, say, C. You have the Euler number close to Z. You have the Hodge polynomial, which we just were speaking about Hodge numbers, but just mentioning last time. So assume K of characteristic 0. Then if X is smooth and say projective, its PQ odd number is just the dimension. So there is a switch between P of Q, which is unimportant since, in fact, this is symmetric, but it's the way one defines things. And the Hodge polynomial H of X by definition it's so you get back the Hodge numbers by just taking the coefficients of monomials in U and V. And it follows from the theorem of the Ligne that H has a unique extension to a morphism in fact, now this result has another proof. I don't have time to say much about this. This is explained in the notes. You have a result of Bittner using the weak factorization, which I already mentioned, and it is stated explicitly in the notes. Gives a very efficient criterion to extend an invariant from smooth projective varieties to K0 where K. This is works only in characteristics 0. And in fact, the criterion is that you should, when you perform a blowing up, maybe not everybody is familiar with that geometric notion, when you perform a blowing up of a smooth subvariety, you should be able to compare, the invariant should behave properly for this blowing up. And that's the only thing you have to check. And usually it's quite easy to check. So technically, using weak factorization, it helps a lot to construct invariants, additive invariants. Question? Another invariant. So I should say something. Say when k is a C. Of course, you can, the Euler number is just the value of the Hodge polynomial at 1, 1. Okay? So that invariant is finer. So another invariant which is even finer than that one, it's involving Chor motifs over K. And it is due to Gillet-Soulet, and also independently to Gulen and Navarro-Aznar. It's always difficult to, because here there are only two guys, so. And so I should explain what is a Chor motif, but I've chosen to explain it tomorrow. Okay? Because we will not need them today, so.
So it's that the invariant should remain unchanged under blowing up?
No, it should behave in a certain way under blowing up.
It almost seems like it should be unchanged because.
No, I can write it if you want, but.
Okay, you don't have to write it, but just if it's.
No, it's just that you have, and then you blow up.
Can you repeat the question?
What is the criterion, the Wittner criterion? And I will answer. So you should have that invariant. Let's call the invariant, I don't know, chi. It's, of course, that you should have chi of x minus chi of e should be equal to chi of e tilde minus k, sorry, it's k of y minus chi of e tilde. Of course, you need that. And usually you just do it by computing everything. And it's quite easy because this guy is just a projective fibration over E, and so usually your invariant is described in a very explicit way. Okay.
So would you have this in characteristic P?
No,
the
no.
Resolution of singularities?
I mean, if you know weak factorization in characteristic P, then it's okay. But so I must say that the weak factorization and also Hironaka result, they are much more difficult than to prove that any other results here. So to use or not weak factorization, it helps often, but when you have another proof, it's simpler, it's not so bad. So now I should mention that, the existence of these invariants shows that this K0 is quite big. Okay. Before going further, I will mention another invariant. Now it's when it's in characteristic P, when K is finite field. Then you have a trivial invariant, but it's very fundamental invariant. You just count points. additional points. And of course, counting points, there is nothing more additive than counting points. Okay? And I will generalize this. It will be useful if K is a number field. Say capital K is a number field. And say S is the variety of capital K. I will consider NP of S. It's what I defined yesterday. So this makes sense only for almost all P. So it does not make sense, strictly speaking, as an additive invariant. Of course, it could make. I could define a big in a big quotient. I could define. It's always the same story because S, I should choose the model, and the number of points maybe depend on the model, but it does not depend for almost all P. So if you want really an invariant, a morphism from Grothendieck ring, from the Grothendieck ring to something, then you should take something ugly like that. Just okay. But we'll need this notation, so I wanted to introduce it. Okay. So now so this ring is quite huge, and very little is known about it. The only non-trivial thing I know about it is a result due to Poonen. So it's in characteristic 0. Is that there are 0 divisors. This ring is not a domain. Okay. And the proof is very nice. It uses abelian varieties. And in fact, it also uses the Bittner's result somewhere. Okay. But now, for the purpose of Motivic integration, we will not really use this ring. Because in the analogy, this ring will correspond to Z. But usually when one computes p-adic integrals, they take place in, you need to invert at least P. So some other ring is needed here. So that's a notation. I invert the class of the affine line. So L for line or for Lefschetz. So the relation here comes from counting points, and the number of points of the affine line is P over FP. So that's where you have this guy. And then, for instance, you don't know so you have a canonical morphism, say theta. And it's not known whether this morphism is injective or not. I would prefer it's not injective, but I hope it is not. And it should be stressed that the result of Poonen is for really this ring, but you cannot deduce anything about MK, because in the proof of Poonen, at a certain moment you factor. So you have to prove that something is non-zero here. And to prove it's non-zero, you go somewhere here. But at a certain moment, you factor through the line. So you get that somebody is non-zero here. So of course, it does not say that it's not zero when you invert L. And there is, so Poonen's proof is beautiful to prove this result, but it does not help to tell you anything about MK. So I want to stress the very difference between MK and K naught of varieties. I mean, they look the same, but inverting L really does something, at least conjecturally. So now I want to mention something which is not directly connected to Motivic integration, but already several people here asked me some questions about it. So it's the following. You take X, a variety over K. Then you can consider the symmetric product. So it's just the Cartesian product of n copies of X. And there is an action of the symmetric group by permuting the factors. And you mode out by this action. Okay? Then you can consider the following series. In fact, this was considered by Kapanov, and in fact in somewhat primitive form a long time ago by Grothendieck in some correspondence with Serre. So you consider the following series. Okay. So I asked the question in a somewhat vague way. There is a result by Larsen and Luns for most surfaces, also characteristic 0. The T is not rational in the K0 as a series with coefficient in this ring. I don't say exactly what it means by rational series in a ring. One can figure out a sensible definition, but I don't want to give it here. Okay? One can also figure out several definitions. Okay. In fact, it's not rational in a very strong sense. That means you send this to a field, and there it's non-rational, and there rationality. When you have a series of coefficients in the fields, then everybody knows what it means to be rational. Okay? So you can say, okay, that's the end of the story. But like a Poonen proof of this theorem, the non-rationality uses the factoring by L. So all these examples by Larsen and Luns, there are more examples. They have for surfaces they can exactly tell when it's rational or not. So they don't survive. So you can still hope. So So I stress this because usually people think that with Larsen-Lund's result, the story is finished. So, and in fact, I'm not sure one can say this is a counterexample to Kapranov's question, because if one look to Kapranov's paper, it's more or less implicit, semi-implicit or explicit that he inverted L. So, okay. So why is this? Sorry.
When you say they can say explicitly when it's rational.
Yes, it's I don't have it in mind, but it's almost never. It's in terms of Kadoira dimension. I think it should be. I don't remember if it's positive or greater than 0. Or
It depends only on Kadoira.
yes, and it's very explicit. I mean, it's for certain I mean, it's equivalence depending on just the Kadoira dimension. Okay.
For curves, is it known?
Yes, for curves it's known. Yes. So why is it interesting? It's because it's a Motivic analog of the Hasselbalch zeta function. So you have the following lemma. So if K is finite field, FQ, then if you apply the counting of points to Z of t, you, maybe I should put x, you get so maybe I should explain what is the Hasselbalch zeta function. So it's this way. And this is just the number of points of x in the extension of degree n. Okay? So it's a simple exercise. The link is you count rational points on the symmetric products xn. So they just corresponding to effective cycles of degree n. And then there is a very easy and well-known inversion formula relating both series, which gives you this result. Okay? And of course, this series is known to be rational by this is a theorem of Dwork. I'm sorry?
So, n of c,
Exp? It's exponential.
no,
Yes, I think the question is, what do you mean by n of A?
In the line above.
The line above.
So n was going from k naught of varieties to z. It was just counting points. It can also be extended to mk to this ring. And this is a series with coefficients in one of these two rings. And I just apply n coefficients wise. And so this is a series say with, of course, with let's say, of course, with coefficient in. But when we speak of its rationality, it's as a series in Q. But okay, don't worry about this. Okay, so this kind of idea, I mean, first having a series with coefficient in Q, and which is known to be rational, and then trying to have a series with coefficient in a ring like MK, which is related to the first one by counting points. In fact, you will see other occurrences of this in the lectures. And of course, if one can prove that this series is rational, I mean, this ring is quite big and naive. I mean, you don't have cohomology. I mean, it's finer than cohomology or anything. So, rationality or knowing the rationality of this series here would mean a very geometric proof of rationality of Assevel zeta function. Because Dwork's proof was beautiful, but uses p-adic analysis. And Grothendieck's proof uses p-adic sheaf machinery. So, okay. So now it's time to speak of the where we will perform Motivic integration. So here the picture is as follows. You have QP, and of course the energy is just taking this field and cause it P. Okay. Of course, I think almost everybody interested in this topic try to perform, for instance, integration over this field. But usually you just say, okay, I know how to perform integration of our locally compact spaces. This guy is not, and so that's the end of the story. And so the great idea is due to Motivic, who realized that one could perform integration on say something like that. With values in MK or something bigger. Okay, hard. So the idea of this is due to Motivic. So maybe I just say what is M hat. So I have this in the picture here. So you view this, usually this is the p-adic integrals that take values in the real numbers. Okay, and so by some infinite process, you may, starting with measures with values in this ring, you may end in this bigger ring. So here you have to make a completion process. So the idea is quite simple. I mean, in the real numbers, p to the minus I goes to 0 as I goes to infinity. So here in m hat, you want something like so you will consider the dimension. So you just define f m of mk to be the subgroup generated by people like I think it's that. I'm not 100% sure. So let's check it. So this means that 1 over Li is in f minus m, and fm plus 1 is contained in fm. Okay, that's okay. So that's the ring filtration. So dimension is multiplicative. So there is a natural process of completion of a ring with filtration. Now there is an issue, is that it's not known whether the canonical map is injective. So just give a name to the image, which is just maybe the same as MK. And there is an easy fact. It's in the notes. Don't have time to prove it, but is that H, and so also the Euler number, factor through MK bar. This means that if I am interested in these invariants like Hodge numbers, I mean they take 0 value on the for people in the kernel, so I'm not so much concerned with the kernel. I'm sorry?
Is MK bar and MK hat the same thing?
MK bar is not the same thing as MK hat. Okay.
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 Sorry, is this difficult to prove?
No, it's obvious. Not obvious, easy. I mean, I can just give you the proof. I mean, if you are of virtual dimension less than something, then your Hodge polynomial is of degree less than something. So if you are in the intersection of all the FMs, then your Hodge polynomial is of degree minus infinity, so it's 0. That's the proof. Okay. And okay. So now I have to define the measure of certain subsets of. Let's consider subsets of in fact, if you say bounded by translation, you can always assume you are here. And I have the idea that you have when you consider the p-adic measure, I mean, one way of understanding it is just saying I know how to the measure of balls. And balls, they are pre-images of points by reduction mode to some power of p. So here, let's do the same. So so here I'm just improvising an oversimplified version of the series, not literally like that. But so no, maybe I don't oversimplify it, and I do this really the theory. So I take x the variety over k, and I'm concerned with the points of x in this, something like that. So my theory will be geometrical. So in fact, there is some scheme of a k-scheme, such that for every overfield capital K of K, the capital K points of Lx, they are just in fact, this does not uniquely define Lx, but let's do, I mean, we will only use this property of Lx. So, of course, if X is a affine space, what is Lx? It's just an infinite dimensional affine space because it's determined by the coefficients of series xi. So I write and Lx is just a spec of this huge ring. Okay. And now, if x is defined by some equation in the affine space, Lx is just the subspace of so if x is defined by, say, f alpha is 0, then Lx is defined by, I just take f alpha of and I write it as an infinite, I expand this into series, I develop. And so what do I have? I have an infinite number of equations on the in terms of the Aj. That's just so replacing power series rings by truncated rings, we get ln of x, and this guy is a finite type. Only because it's the same story here, except that you only look to a finite number of to a certain order in T, so you have only a finite number of AGIs occurring and a finite number of equations. Okay? Helix is not a finite type. And you have a truncation morphism from Lx to ln of x. So to speak to a power series, you just assign its truncation. And this is a morphism of varieties. Now, yes?
Why did you say this isn't unique? It looks like some adjoint functor as well.
Yeah, but as a scheme, it's not
Repeat the
different.
question?
The question is why is not Lx unique? I mean, to have Lx unique, you should ask it to represent a functor, and then I only define it on capital K points and not on marginal points. But it's completely irrelevant for what we're doing. So, assume what? Assume X smooth. So you have the idea is following is we want to do the analogy with balls. So take C in ln of x. Maybe C is not a good name. Say A. Constructible subset. So they were already introduced. I think they are just constructible in the sense of Chevalet, so they're also definable in a certain sense. And in the algebraic geometry language, they are just they're just Boolean combination of locally closed varieties, and it can be written as a disjoint union of locally closed varieties. So, remark, this guy has a well-defined class in the Grothendieck ring of varieties. The Grothendieck ring was just done for that. I mean, you just cut A into pieces, and you add up the corresponding classes, and by additivity, it does not depend on the way you have cut A into pieces. Okay. Now we consider C the inverse image of A. So this kind of ball, but here we call it cylinder. And you want to define its measure. So we just take the class of A, but imagine we are in the p-adic case. So A would be, for instance, a point. Okay. Of course, we have to renormalize this by a factor denominator with p to some power, n times the dimension, or n plus times the dimension. So here we do the same. Just do this with d dimension of x. And that's okay, right? Because of course we could represent C as a pre-image of some at some other level. I mean, if say A prime is a pre-image of A in ln plus 1 of x, then C, of course, is Pn plus 1 inverse of A prime. So we should check that you have this equality. And I say it's okay because here I assumed x smooth. I say this morphism is a fibration, Zariski fibration. With fiber, the affine space of dimension d. Okay, this is very easy to check. Imagine, for instance, X is just the affine space. Then it's okay. We have a description of these guys in terms of affine space, and here we just have d more variables. And in general, X being smooth, one can, I mean, there are several easy proofs that this is a fibration. I mean, it's just using smoothness in an easy way. Okay? So we defined volume of cylinders. And of course, this is okay, but in fact, I think I will not explain what we do more generally in details, but we can measure semi-algebraic subset of the arc space. So So let me explain what it means. So I give only assume X is just the affine space. Then I consider path language. So there are three sorts. First sort is capital K valued field. Second sort runs over small k as the residue field. And the third sort over gamma, the value group. Here you consider the ring language. Here also the ring language. Here's the Pressburger language. And you add, what do you add? You add the valuation. And you add something more strange, but which is unfortunately very important. It's the angular component. I think the terminology is terribly bad, but it's too late to change. It goes from k to small k. So assume you have a symbol for the uniformizing parameter, and it's just to some element x here. It associates the residue class of, let's call t the uniform parameter, t to the power minus val or v of x in k, and 0 if x 0. So that's path language. So if K is characteristic 0, question?
There might be a possibility to avoid the angular component map, but maybe you already considered it. There is a language of François Loeser,
Yes, yes.
which is some generalized language of McIntyre, and it might be possible to use that instead of the language of Pascal.
I mean, for instance, when
It's more difficult, I suppose.
yes, but when, for instance, K is C, is a complex number, small k, then you can avoid the use of AC as far as I remember. But I mean, let's do as if we were not concerned with.
What is T,
T is just a name for the uniformizing parameter.
which is fixed and belongs to that?
I mean, now I will use it only for power series rings where you know exactly what T exactly means T. I mean, okay. I'm not able to sustain a precise conversation about logics. I mean, I'm really not an expert. I mean, I don't know. I don't master the vocabulary so well. So. Okay. So then you take K to be KT, and you have elimination pass. You have a theorem by path stating that you have elimination in of quantifier. And so semi-algebraic subsets of X, of Lx, in this case are just definable subset in path language. There is some subtlety here that you don't take only you don't take only power series with coefficient in small k. They can be with coefficient in any extension. Okay. Okay, and then you have a measure these semi-algebraic subsets. They have a measure in, let's say, m hat, in fact, in some smaller ring. So I just take 5 minutes to. In this theory, we have a very basic it's a fact. I mean, in the first lecture, I explained the important role of the change of variable formula, which is quite almost obvious over the p-adics. And here, it's less obvious. You have the following theorem. I mean, it was proved by Denef and me. It was, I mean, stated in some form by Motivic, but I mean, the proof nevertheless requires some work. There are several ways to express several variants of this theorem. So in fact, I must say that here I don't present the more recent and general theory of Motivic integration. I mean, I am currently developing, I think, somewhat final framework for the theory with Ralph Kluckers. And I hope to be able to lecture on this soon. So, in fact, all these statements, they have better versions, more flexible, more general. I just explain particular cases. So, consider h from y to x by rational proper. So it's a morphism of varieties. With x smooth, y smooth. Maybe x not smooth, but anyhow, I did not explain anything about Motivic integration in the non-smooth case. So take a subset of Lx miserable. Alpha, so let's say I'm using the n function. So I should explain what it means, what I mean by such integrals. So I more or less explain volumes. So by this I mean it's like in the p-adic case. By definition, so I've assumed that the values of alpha are positive. So I take the volume of the locus of where alpha is a text value I. So by definition, I mean, when I write this, I assume it makes sense, so that these guys are measurable, and that this series converges in A mat. So this is the meaning of such expressions. So, and I should explain briefly what is this. And